What's up, guys? It's Ben at EFI University, and I'm back for another Emtron training video for you guys. Now, on the dyno here, I have my 511 cubic inch Ford Stroker Godzilla engine. 7.3 liters, what it used to be. Now it's, I don't know, however many liters 511 cubic inches is. But it also has some cool ITBs and a dry sump, so it's a pretty stout engine. Makes a bunch of power. In fact, I spent a bunch, like 70 dyno pulls over the weekend, finding out not only exactly how much power it made, but also how much friction it had. Because one of the great features about the Emtron ECU is the way that it can calculate the torque and the power that your engine's using. Now, a lot of people want to talk about things like torque management and torque control and, TMF and all these fancy features. But the thing you got to know is if you don't have all of the ECU model done correctly to actually match your engine, then you're really not going to be able to use the torque management correctly and effectively. So in order for you to dial in and tell the ECU, hey, limit my torque to some number, 500 foot-pounds or 700 newton meters or whatever value you want to use there, you have to know a couple of things. First of all, how much torque does it actually make for real? And then second of all, how do I limit that torque? And there's different ways you can do that by limiting the throttle area or the ignition timing or doing rev cuts. But you really can't do any of those things with any kind of precision until you've made the model correct. So I want to share with you a little bit about how I go about doing that. My way is a little bit more technical, a little bit more involved than what most people do. But what I wanted to see is if I could get the data in the ECU to actually match my dyno. So we're going to take a look at a couple things here. So I have a data log pulled up on the Emtron ECU from my PC log. And so if you come in here, I'll show you what I got. I got it real simple. Right now, what I have is the engine speed, the RPM from the dyno pull on both pages here. At the top, I have the mass airflow shown in two different ways. The white line here is showing me the air mass final calculation that's in grams per cylinder, or in other words, grams per induction. And then the blue line, I have the same value, but showing me grams per second. So let me talk to you about why. Essentially, when you look at an engine's torque curve, which by the way is what I have down there and below and what I have on the dyno, the torque is really showing you how well you filled the cylinder with air per engine cycle. Whereas power is a function of time. That's why it's always torque times RPM. When we look at our airflow in time, you get grams per second, which we could easily convert into other units like pounds per minute, pounds per hour, whatever. But grams per second is like the total amount of airflow over time, whereas grams per cylinder or grams per induction is the amount of airflow that we got for every individual cylinder filling there. So what's interesting is if you look again at the air mass final that's in grams per cylinder, you'll notice here that the grams per cylinder shape has the same exact shape down here as the engine's torque calculation. So that makes sense. Whereas you'll notice that the engine speed line is followed very closely by the air mass flow because it's time-based. But here we are, we're at 6,183 RPM. I have an air mass final of 1.349 grams per cylinder and a mass flow final of 559 grams per second. So if I do a little math on my calculator, I could go, let's see, that's 559 grams per second. So times 60 second gives me the total number of grams per minute. And then if I was to divide that minute by the number of inductions that happen, so I'd be 6183. So let's see, I need to do cycles, so it's roughly half of that. So it'd be what, 3,000. Let's see, let me do a little math here. So 6183, divide that by 2. I'm doing 306. Sorry, I think I did that wrong. 6183 divided by 2. There we go. 3091.5. I'm going to write that down. 3091.5. That's cycles per minute, right? So if I go back over here, I got 559 grams per second times 60 seconds. That's the total number of grams per minute. I'm going to divide that by 3091.5 cycles. And that's going to give me 10.85-ish. Then I'm going to divide that by the number of cylinders to get 8 cylinders. And I get 1.356, or really close to my 1.35, 1.349 grams per cylinder. So a little bit of my rounding there, but you can see where that number comes from. The white line, airflow final in grams per cylinder is grams per induction. That curve is going to follow the engine's torque curve. And then of course down at the bottom I have torque, but my airflow mass final in time-wise is going to follow your engine speed. In other words, it's just going to keep going up and scale with your engine speed. So what I want you to see here is I took the time to map out the engine's model using my Emtron. In the torque tuning parameter there, you're going to find a table that's called frictional loss table. So what happens is when you tune the engine, the Emtron will then take the values that you put in and estimate or calculate very accurately how much torque and how much power the engine made. But that can only be true if you do two things. Number one, you have to get the volumetric efficiency correct, because the torque output is highly dependent on the engine's volumetric efficiency. So when you go to do your tuning, you have to make sure you get your fuel injectors characterized properly, your fuel pressure set properly, your fuel pressure differentials being measured. And so your table here is volumetric efficiency. Remember, your volumetric efficiency of the engine's got to be right, and then it's not going to change as you change altitude or barometric pressure or whatever. What's going to happen then is the density is going to change, and of course the ECU is measuring the density through pressure and temperature. So in order to calculate the correct amount of airflow, you got to get the volumetric efficiency right first. Once you have that right, and you'll know because your lambdas are on target. So take a look at my log here. I go to engine health. Down here, I've got a pretty reasonably accurate lambda here throughout the run. And you want to make sure that you're getting this without a ton of closed loop correction. If you're 10 or 20% off there, then obviously your volumetric efficiency is not going to be correct, okay? Once you get the lambdas correct, now you're going to go to your spark table and you're going to make sure that you have the correct MBT, or minimum best timing for maximum best torque, because the calculation of the ECU is deriving torque based on the assumption that you put the right numbers in the spark table. So if you don't get the spark table right and you don't get the VE table right, if you just toss numbers in there and kind of be close, well, then your torque output's just going to kind of be close. But if you want it to be really precise, you got to get those two things right first. So when I say precise, what do I mean? Well, let's take a look here. If I come back to my page, I can go to almost any RPM. Now, you got to remember that the torque value that you're going to see here in the table is uncorrected. So on the dyno, the torque number that you get is corrected to the weather station, the barometric conditions. So I can do one of two things. I can either take the torque value from my ECU and multiply it times whatever the correction factor was on that day. For example, that day I had 6.75% correction. The weather in the room where I was testing was 6.75% worse than it would have been if I had been at sea level on a standard J607 SAE type of day. So I can either take the torque in the dyno and multiply it times that, or I can turn off the correction factor in the dyno. So either way, for now, I'll tell you what, I'll just turn it off. So now I have uncorrected data here. And what I'll do is I'll scale it around until my engine RPM here is 6180, and I was making uncorrected 627 foot-pounds on the dyno. So if I go to 6180 in my log, what you'll see is here's 6183, and the torque is 627.5. Pretty dang close, right? So now if I change the RPM over here, let's go down to like, say, 4800 or something. So I'm 670.9, call it 671. That's the torque that the ECU is generating. If I come over here, same RPM, 4,800, I am 667 foot-pounds. So 671, 677, we're within single digits there. So then I'm going to go over here to 3,500. And at 3,500 RPM, I'm going to see what torque I have here. And I got like, 585. So I'll go over here to about 3,500. And I have 585. So let's talk about this for a minute. You got to understand that there's a couple of different values that the ECU is going to give you. One is it's going to give you the theoretical amount of torque that the engine made in the cylinders. That's called engine torque ideal. And then you're going to get this engine torque final. And you could get it either from your speed density or your TMF calculations, or a number of ways to blend those together. But ultimately, the ECU starts with, do I have the correct airflow? It assumes you do. So if you do, it will then generate a torque value based on the ignition timing you have, and it'll output that. But the problem is the value that it outputs for ideal is before all the frictional losses. So this number here that's called engine torque is the output of what you should see on the dyno. So you can see that mine matches really well, because what I did is I went on the dyno and I would make a dyno pull and it makes what it makes. If I look at the engine torque ideal value and then compare that to the frictional loss table, it should be the ideal torque minus the frictional losses equals this torque. So if this torque doesn't match, the problem is that I haven't correctly identified the frictional loss of the engine. So come over here and I'll show you how we do that. So if I come over here and I'm going to go to the tuning tab and I'm going to go to torque and I'm going to have the frictional loss tables. So when you go into this table, it's basically just engine speed based. And this is, in my case, I have the units as foot-pounds. So I'm just entering in at each RPM the difference between the engine torque ideal and the output torque to make the output torque match my dyno. So it's actually really easy to do that. But once you have those where they match really well, now you've got a good model of the engine's friction. And until you have that, it's going to be really hard for you to call out a torque value and say, do this or do that, and do it with any accuracy. Now, of course, there's correction tables because you're going to find that the frictional losses are higher. Say, like, if you have really thick oil and it's a cold morning and you want to start up and go racing right away, well, you're going to get some more losses there. So you would do that with an offset table. Things like on this engine where you have individual throttle bodies, it's tricky because the throttle bodies are so big that even when I close the throttle, halfway or down to 40%, you're still going to get roughly barometric pressure, which is a higher value than what the engine's actually seeing. And so the ECU then can't effectively measure the real, let's call it vacuum down by the intake valve. So it sort of overestimates how much torque you're making there. So in that case, what you can do, or what I did, was I just clamped the throttle opening to 25% and 50% and 75%, do a dyno run, and then do a torque correction for those tables. And I think I can show you those. If we go down to torque correction tables, I've just got corrections for each effective throttle area and each RPM. Depending on the resonant harmonic wave that's moving through you, you're going to get more or less correction value here. Those are percent corrections. So again, you would just go back to your log and you would say, what is my actual torque showing me? And what is the dyno showing me? And you would offset your friction and your torque correction tables until you get that right. So now, once I've got all that called out, I can go into my user demand and say, limit the engine to 500 foot-pounds. And then as long as the engine will at least make 500 or more, it'll find the right ignition timing and the right throttle angle to go in there and limit the torque. But if you haven't really done all this correctly, what happens is guys just put in like a fudge factor. They just move the numbers up or down until it makes the car do what they want. And then the number's not that precise. But doing it this way, you can get a much more accurate representation of what the engine's doing. But these values, you'll know if they're right because they're going to do a good job of matching the dyno. For example, if I go in here, I can tell you that we have a measurement we call brake-specific air consumption, which is roughly about every 10 pounds per minute of mass airflow will give you about every 1 pound per minute of mass airflow will give you 10 horsepower. Roughly, that works out to about 7.57 grams per second. Horsepower for grams per second. You can work out here, but let's try it. So if I go up here and pick any RPM, I'll just kind of pick for example, here's 4,800. So at 4,800 RPM, it's showing me a mass flow final of 450.8 grams per second. So 450.8 grams per second times 60 seconds gives me 27,048 grams per minute. There's about 454 grams in a pound. So that gives me 59.57 pounds per minute. If I can make 10 horsepower for every one, I should be somewhere in the neighborhood of 595 horsepower at 4,800 RPM. So if I go over here to 4,800 RPM on my dyno, I'm about, instead of 596, I'm about 610. So I've got a little tiny bit of rounding error there. But again, this is an uncorrected number, and I still have to go through the weather correction and add all that back in if you want to make it perfectly match the dyno. You should be able to get your torque curve on the data log to be within single digits, to make a run on the dyno and make a run in there. If you can do that, you're going to be able to call out the correct amount of torque and actually limit the vehicle to do the things you want. So I hope that was helpful for you and you have a little bit better understanding of how the torque model works in the ECU. But just remember the basics. Tune your VE table correctly, tune your spark table correctly, and then offset the frictional loss table to make your data log match your dyno.